welcome. My name is Elizabeth Stevens, and I'm joined by Mark Sherman and Daniel Williams. And together we worked on Hayward's wireless poolside multi-sensor system project. Our technical directors were Jamie Murdoch and Joe Bendel. So our project was motivated by the current system limitations of the existing pool controller system, namely that all environmental parameters must be measured with wired sensors, and specifically with the water temperature sensor, the pool filter must be turned on to measure temperature. This requires advanced user scheduling when the user wants to, for example, heat their pool, as they must ensure that the water temperature sensor is on and the pool filter is turned on. Also, the pool cover is not allowed to be operated by the system and must be manually operated by the user due to safety concerns. And this actually causes a lot of issues where the pool cover will be closed and the user forgets to turn off their water features that were scheduled to turn on in 2 hours, and then they dump gallons of water on their pool cover and actually destroy it. So our system would provide advanced feature automation, specifically with the landscape lighting, pool cover detection, water level detection, and autofill capabilities. And so this would provide an improved user experience and a decreased operating cost due to less user interaction and a greater automation of tasks. So our best outcome as laid out for us in September was to create a 2-unit concept system which transmitted sensor data via radio connection, employed power-saving methods, interfaced with the existing pool controller system, operated in a wide temperature range, and fit in a sleek plastic enclosure. So the poolside unit would measure environmental parameters such as air temperature, water level, ambient light level, and pool cover status. It would be battery operated and would sit in the pool itself. The receiver unit would interface with the current pool control system, shown here, and it would process received sensor data to automate features. So we can actually proudly say that we've achieved our best outcome as we've designed a poolside sensor unit proto board, worked with a mechanical engineering student to design a sleek plastic enclosure prototype, and designed a receiver proto board as well as the pool controller interfacing circuits to go along with that. I'll now hand it over to Mark to talk about our hardware achievements.
Thank you, Liz. So, along with meeting our best outcome, we had many hardware achievements that we're very proud of. Our 2 major ones were our pool cover detection methodology as well as our PCB layout. So for our pool cover detection methodology, we decided to go with a low-cost IR and ambient light combo sensor. We chose this as it had lower power consumption in regards to the battery powered out system, and the ultrasonic distance sensors typically drew more power. Also, this sensor took into account low reflectivity of the pool cover, possibly being a black or dark navy color. And as you can see here, pool covers can either be mounted below the pool coping or above the pool coping. So after extensive research on typical water levels and typical pool level coping measurements, we decided to angle our sensor board, shown here, so that we can provide line of sight measurements for our IR ranging sensor. That way we can detect either pool cover method, regardless of where it is in regards to the pool coping. Also, the angle here provides a slope for water droplets to roll off of, combined with our hydrophobic window for our sensor. That way we can have less interference from water droplets on the infrared beam. Our second major hardware achievement was our PCB layout shown here. At the top, we have our RF antenna, which is used for our radio communication to our receiver base station. We have our microchip controller here in the center, used to control the device. We also have our 2 external crystals for our real-time clocks for the microcontroller, as well as the radio. And finally, we have our debugger and our binary mouse that run the length of the board. So this second board seen here on the top is blown up in this image here. We have our IR ranging navy light sensor at the top, our 2 interfacing LEDs so that the users can get feedback when pairing the device or actually interfering with the device at the poolside, which I'll go into a little bit later. We also have our air temperature thermistor right here, as this part of the device will be mostly out of the water, giving us our most accurate readings for air temperature at the poolside. Finally, on the back layer of the board, we have our CapSense button for our user interface, so users will be able to directly interface with the device at the poolside, so things like turn the lights on and things like that. Also, we have our capaciting water level sensing strip here. As the water level increases along the side of the device, it actually increases the capacitance on the line. That, when compared to our reference sensor on the back of the board, we'll be able to tell where the water level is in regards to where the board is mounted in the pool. And obviously, along with our hardware achievements, we've had many software achievements. So I'll hand over to my friend Danny to tell you about that.
Thank you, Mark. So on the software side, we have achieved our best outcome in 3 critical areas. The first is in radio communication, where we have achieved a major pillar of our best outcome of transmitting sensor data over a long distance. All of our software development has been done for Atmel's new SAMR 30 radio and microcontroller combo package. This combo package, along with Atmel's MyWi network protocol, has allowed us to set up a simple 2-device personal area network where our receiver base station is the PAN coordinator and the Poolside sensor unit is an end device. This serial communication window allows us to see an example of the data received at the base station, which is then sent to the existing pool controller to control pool features. You can see an alert of whether the pool cover was detected, an ambient light value in lux, and the 2 temperature values read at Poolside and degrees Celsius. The next area is sensor communication, where we have conceptualized and implemented the ways in which we will measure our 5 desired environmental parameters. Air temperature and water temperature are measured by reading a voltage across a thermistor through an analog to digital converter. Ambient light and pool cover detection is done with a single I2C sensor, and water level is sensed using the capacitive sensing layout that Mark described earlier. All of these have been implemented in software except for water level due to the fact that the SAMR 30 is a new chip for Atmel and does not yet have support for capacitive sensing code. And finally, we have made major strides in meeting our goal of lowering the power consumption of the Poolside unit to meet our goal of having that device last a full 5-month pool season on a single set of batteries. Using the low power capabilities of the SAMR 30, we have programmed the processor to be put into a low power standby mode in between sensor reads. And we've also been in constant communication with microchip application engineers, microchip now owning Atmel, to put the radio into the lowest possible sleep mode between sensor reads. This graph shows that these efforts have allowed us to lower the current consumption of the device to 680 microamps between sensor reads and 1.5 milliamps when reading sensors. And using an online calculator, we were able to calculate that this power scheme allows the device to last 275 days or 9 months on a set of 2 AA batteries, which is well over our goal of 5 months. So all of these software achievements taken together with our hardware achievements allow us to confidently say that we have met our best anticipated outcome. So finally, we'd like to just extend some special thanks to a few people, our technical directors, Jamie Murdoch and Joe Gundel, for all of their time and effort in helping us meet our best outcome. Dylan Fontaine, a mechanical engineering student here at URI, who designed and 3D printed our Poolside sensor units enclosure prototype. Application engineers at Microchip, who provided support with the new SAMR 30 chip. And Professor Sunak for all of his work in making this program the best it can be. Thank you, and we look forward to seeing you at our demo.